This little chip, barely the size of a coin, has to survive being kicked at over 60 miles an hour, header after header, match after match, and it's inside every single ball used at the 2026 FIFA World Cup. But here's what almost nobody knows. The factory that builds these balls, chip and all, isn't anywhere near a stadium. It's not even close. Today, we're going inside. A World Cup ball looks simple, round, colorful, familiar. But the ball used at the 2026 tournament is unlike anything FIFA has ever used before. It's connected, packed with sensor technology that helps referees make calls in real time, down to the exact millisecond a player touches it. What you're about to see is how that ball actually gets built, from raw panels and precision stitching, all the way to a finished, chip-embedded match ball ready for the world's biggest stage. Coming up, we're going inside the massive facility responsible for producing every single one of these balls. But there's one specific moment in this process where a tiny piece of technology has to be installed with zero room for error, or the ball simply won't work the way 48 nations are counting on it to. We'll get there. Let's start from the beginning. Let's start with the part that makes this ball completely different from every World Cup ball before it. For decades, a World Cup ball was just leather, panels, and air. Beautiful engineering, sure, but fundamentally simple. This one isn't. This one has to survive being struck at high speed, headed, dropped, dragged across wet grass. And somewhere inside it, a tiny electronic sensor has to keep working through all of it, recording data 500 times every single second. That's not a small engineering challenge. That's a contradiction the factory has to solve. Build something durable enough to survive a 90-minute match at full intensity, while also protecting something as fragile and precise as an embedded electronic chip. So how do they actually pull that off? It starts long before the chip ever enters the picture. Every match ball begins as flat material, specially engineered polyurethane panels designed to be lightweight, weather-resistant, and structurally consistent. And here's something that surprises people right away. This ball isn't built from the traditional 32 panels you'd recognize from older World Cup balls. It's built from just four panels. The lowest panel count ever used on a World Cup ball. And that number isn't arbitrary. Fewer panels mean fewer seams, and fewer seams mean more predictable flight. Every seam on a football is a tiny disruption to airflow, a place where the ball's surface isn't perfectly smooth. Reduce the seams, and you reduce the unpredictability. For players, that means a ball that flies exactly where they expect it to, shot after shot, match after match. But four large panels create a different challenge: precision. With fewer seams to hide small errors, every cut has to be exact. The panel material gets cut using automated cutting systems calibrated to extremely tight tolerances. A shape that's off by even a fraction of a millimeter can throw off the entire geometry of the finished ball. Once cut, the panels get surface textured, debossed with subtle patterns that most fans never notice on TV, but that matter enormously on the pitch. These micro and macro textures are engineered specifically to improve grip in wet or humid conditions, and to stabilize the ball's flight when it's struck hard or with spin. It's a small detail, but it's one of dozens of small details that separate a professional match ball from something you'd buy at a sporting goods store. Here's where things shift from cutting to construction. Instead of traditional stitching, the kind you'd associate with footballs for generations, this ball's panels are joined using thermal bonding. Heat and pressure are applied precisely along the panel edges, fusing them together into a single, seamless structure, rather than sewing them with thread. Why does this matter? Stitched seams, no matter how well made, create tiny gaps and slightly raised edges. Thermal bonding eliminates that. The panels fuse into one continuous surface, with no thread, no needle holes, no weak points where water or pressure could eventually cause separation. The result is a ball that holds its shape more consistently and performs identically match after match. Something that matters enormously when officiating decisions are going to depend on the ball behaving exactly as expected, every single time. The bonding process itself requires intense quality control. Temperature has to be precise, pressure has to be even across the entire seam. Workers and automated systems monitor each bond as it's created, because a weak bond doesn't just risk failure. It risks inconsistency, and inconsistency is the one thing this ball cannot have. Now we arrive at the challenge we mentioned earlier. Somewhere inside this nearly seamless, perfectly balanced sphere, a sensor needs to be installed, not bolted on, not strapped to the outside, embedded, invisibly, permanently, without disrupting anything about how the ball flies, bounces, or feels. Think about what that actually requires. The sensor has its own weight, small but not zero. If it's placed without compensation, it shifts the ball's center of gravity slightly, which would make it spin or fly differently depending on which side gets struck. For a ball that's going to be used in literally the biggest tournament on Earth, slightly different, isn't acceptable. It has to behave identically no matter where contact happens. There's also the matter of protection. The sensor is an actual electronic device, sensitive components, a small processor, and a tiny rechargeable battery, all of which need to survive repeated high-speed impacts without failing. So here's the question this factory had to solve. How do you put precision electronics inside a ball that's going to get kicked as hard as humanly possible, hundreds of times, without the ball flying differently or the sensor breaking? The answer is genuinely clever. The sensor doesn't sit rigidly fixed against the inner panel wall. Instead, it's mounted inside a specially engineered suspension system, a structure designed to absorb and distribute the shock of impact, protecting the delicate electronics inside from the force of a strike, a header, or a hard bounce off the turf. And to solve the balance problem, engineers added small counterweights into the other panels, positioned specifically to offset the weight of the sensor itself. The result is a ball where the center of gravity stays exactly where it should be, regardless of where the sensor sits internally. Players can't feel it. The ball doesn't curve differently. It doesn't bounce unevenly. From the outside, in terms of pure feel and flight, it behaves exactly like a ball with no electronics inside it at all. This is the stage in the factory where the installation happens. Carefully, by hand, under inspection. Each sensor gets seated into its suspension mount, secured, and verified before the ball moves forward in the production line. Workers check alignment. They verify the housing is sealed correctly, because once this ball is fully assembled, there's no opening it back up to fix a mistake. Once the sensor is secured inside, the ball moves toward final sealing. The remaining structure gets bonded completely shut, locking the sensor, its suspension system, and the internal bladder all into place. From this point forward, the ball is a closed system, durable, sealed, and ready for the next stage of testing. The bladder itself, the inner component that holds air pressure, has to be installed with precision as well. It needs to sit centered, evenly inflated, providing consistent pressure across the entire interior surface. An unevenly seated bladder creates a ball that bounces or rolls inconsistently, which is a problem at any level of football, let alone a World Cup final watched by hundreds of millions of people. Before any ball leaves this facility, it goes through extensive testing. Pressure consistency gets verified. The ball gets struck repeatedly by mechanical testing rigs designed to simulate real match conditions, high-speed strikes, headers, and bounces over and over, while engineers monitor whether the sensor continues transmitting data accurately and whether the ball's flight characteristics remain stable. This is also where the connectivity itself gets validated. Each ball's sensor has to wirelessly transmit motion data reliably and instantly, because during an actual match, that data feeds directly into officiating systems used to make real-time calls. A sensor that lags, drops signal, or transmits inaccurate data isn't just a manufacturing defect. It's a decision that could affect the outcome of a match watched by the entire world. So testing isn't a final formality here. It's one of the most rigorous stages in the entire process, because by the time a ball reaches the pitch, there's no second chance to get it right. Only after a ball passes every performance, durability, and connectivity test does it move into branding and final visual inspection. The colors representing the tournament get applied with exact placement standards. Every logo, every design element gets verified for accuracy and positioning. And then, finally, each ball gets one last full inspection, visual, structural, and electronic, before it's cleared for shipment to stadiums where it will be charged, tested again on-site, and ultimately placed into play in front of millions of fans. And somewhere in that facility right now, another ball is moving through these exact same stages, destined for a moment in this tournament that nobody can predict yet. A goal. A controversial offside call settled instantly by data most fans will never think twice about. A piece of football history, quietly built inside a factory most people will never see. Here's what's really worth sitting with. This ball started as 4 flat panels, nothing more. It got cut with extreme precision, bonded without a single stitch, fitted with a sensor that had to be hidden perfectly, balanced, and protected, all without changing how it flies, spins, or feels in a player's hands. And by the time it leaves that factory, it's no longer just a ball. It's a measurement device disguised as one. Think about what that actually means for the game itself. A goal line call. An offside decision. A handball nobody can agree on. All of it now settled, in real time, by something built into the very object players are fighting over on the pitch. That's not a small leap. That's a fundamental shift in how the world's biggest sport gets officiated. And it all starts here, on a factory floor most fans will never see. The next time you watch a controversial call get reversed in seconds, remember, That decision didn't come from a camera angle or a slow-motion replay alone. It came from this. From 4 panels, 1 chip, and a level of precision most people never even think to ask about. If this kind of hidden engineering fascinates you, hit that like button, subscribe, and stick around. And if you enjoyed this one, go check out our video on how every single Super Bowl football gets made. Same obsession with precision, completely different sport, equally wild process. Drop a comment below. Tell us which sports manufacturing video you want to see next. Your suggestion might just become our next video. See you inside the next one.